So in this video, we're going to show an example of estimating the area under a curve using left endpoints. Before we dive into it, we want to identify why we want to estimate the area under a curve. So in calculus so far, we've dealt primarily with derivatives. And what we've identified is that the derivative tells us the instantaneous rate of change or the slope of the tangent lines to a curve. And what we're going to discover as we flesh out our theory of antiderivatives is that antiderivatives can be used to aggregate or accumulate, add up change, and that the aggregated or accumulated change is represented by the area under the curve. So we have derivatives giving us instantaneous rate of change, and antiderivatives will wind up being a tool to give us aggregated or added up change, and that change is going to be the area under a curve. So we're going to be interested in finding for a curve. In this case, I have the curve f of x equals negative x squared plus 2. We're going to be interested in being able to find the area under the curve over a given closed interval. But before we can develop the theory of finding the area under the curve and then explaining why it means something physically, we're going to need to look at how we would estimate the area under a curve, because the theory of estimating the area under the curve will be used to eventually calculate the exact area under the curve and identify what the meaning of that area is. So here I have the function f of x equals negative x squared plus 4, and we're going to work over a closed interval from 0 to 2, and we want to estimate the area under the curve. This is the same curve that we saw on the previous slide. We want to estimate that area using 4 rectangles and left endpoints. So we'll just talk through the process of doing this. So the first step in the process is to look at the line interval you're working over. So I'm working over the interval on the x-axis from 0 to 2. And what you want to do is figure out what your delta x is. And delta x is just going to be the width of each of your n rectangles. In this case, we have 4 rectangles. So it's pretty customary to represent the number of rectangles with the letter n. And so in this case, I'm letting n equal 4. And we need to know delta x, which is the width of an individual rectangle. So to find the width of individual rectangles, so delta x, the width of each individual rectangle, all you do is take the right endpoint or the right bound of your closed interval, you subtract your left bound of the closed interval to get the length of the line of the total line segment you're working with on the x-axis, and then you divide by the number of rectangles that you want. So in this case, I want 4 rectangles. So I do 2 minus 0 is 2. The length of the line segment is 2. And I want to divide that length of 2 into 4 pieces to get 4 rectangles. So this simplifies to a half. If we were doing this generically, we would say, hey, I'm working over the closed interval from A to B, and I want n rectangles. You would say delta x is equal to b minus a. You take the right bound of the line interval minus the left bound of that closed interval, and then divide by n the number of rectangles to get the width of each rectangle you're working with. So this would be a generic representation of delta x if we didn't know how many rectangles we wanted up front or the interval over which we wanted to work. So this is the first step. Just figure out what the width of each rectangle will be, and then go in on your interval from 0 to 2 and label the numbers in that you're going to need to work with. So if we pretend we don't see rectangles yet, what I would say is, hey, I want to start at 0, and whatever the denominator is right here, in this case the denominator is a 2, I'm going to put this 0 over a 2 because 0 over 2 is still a 0. And then to get to the next tick mark, you just add the width of your rectangle to it. So I'm going to go 0 plus a half is a half, and then a half plus a half is 2 halves, and then a 2 halves plus another half is 3 halves, and then 3 halves plus another half is 4 halves. And I don't want to reduce any of these fractions. I want to leave them with in a common denominator form, and you'll see why in a minute, with my denominator being the denominator in the width calculation I have for each triangle. So if we then look at the differences between any two numbers, a half minus 0 halves, we'll get that our delta x is a half. 2 halves minus 1 half is a half. 3 halves minus the 2 halves is still a half. And 4 halves minus 3 halves is still a half. So by starting with the first number on the closed interval and then adding a half plus a half plus a half plus a half, we get rectangles. We're going to wind up with rectangles, each of which has base 1 half. If I were in this generic form where I was working over the closed interval from A to B, once I found my width, I would just take the first number plus delta x to get the second number, and then I would do the first number plus 2 times the change in x, and so on and so forth. So I just add multiples of my delta x to a, where a is the left bound of the interval. So that's step 2. Step 1, find the width of each rectangle. That's the length of the line segment divided by the number of rectangles. Determine that. Step 2, label the numbers you're going to be working with onto the x-axis by starting with your left bound and then adding the width of each rectangle to that number until you've labeled all the way out to the last number on your line interval. So this is the closed interval from 0 to 2. So here I stopped at 4 over 2, and 4 over 2 does equal 2. So I have every number from 0 to 2 labeled in terms of increments of 1 half. And then you're ready for step 3, which is to actually create your 4 rectangles. And in this case, it says use left endpoints. So all a left endpoint means is start at the first number on your closed interval and put your upper left corner of the first rectangle on the curve or the graph. So in this case, it's the graph of negative x squared plus 4. So I would want to find the point right here, right at the start of the curve, and I would construct a rectangle whose upper left corner, it's a left endpoint, so the upper left corner of the first rectangle needs to be on the curve, starting at 0, the first number on the curve. So this ordered pair right here is going to be input 0 over 2, or input 0, and then the function output right there is going to be f of 0 over 2. And then you draw your first rectangle based on that. And you can see that's going to give you an overestimate of the area under the curve on that interval from 0 to 1 half. And then you create your second rectangle using a left endpoint. And that means go to this point on the graph, go to the input your next number, input your 1 half, which is your next number. Get the function output there. That's going to give you a point on the curve, and construct a rectangle using that point. And the upper left corner, because it's a left endpoint, the upper left corner of the rectangle you construct should be on the curve. And then you're going to move over to your next number on your that you've labeled onto your x-axis. You're going to input the 2 halves into the function to get the function output there. That's going to give you an ordered pair. You're going to construct a rectangle, drawing that down to the next number so that we get widths of 1 half. And that's going to give me the upper left corner of that rectangle is on the curve. And then you step down. This is rectangle 1, rectangle 2, rectangle 3. I wanted 4 rectangles. So now you go to the 3 halves, the next number you've labeled in on the x-axis, the 3 halves. You evaluate the function at 3 halves. That gives you a point on the line, and you draw a rectangle based on that point. So you wind up with a rectangle whose upper left corner, upper left endpoint, is on the curve. And then notice that the last number on the closed interval, the 2, we don't need to use it to construct a rectangle because I have 4 points on the curve. that I've used to construct 4 rectangles, and 4 rectangles is all that we wanted. And then what you want to do is calculate the area of each rectangle. So notice that the area of the first rectangle, because it's a rectangle, it's going to be the height of the rectangle times the width. But the width of each of the 4 rectangles by construction is just a half. And the height of the rectangle is actually the function evaluated at 0, or at 0 over 2. So remember, the y-coordinate gives you the height. So the area of this rectangle is just going to be f of 0 over 2 times a half. And then you can say, hey, I want to find the area of this rectangle. I'm going to use it to represent the area under the curve between 1/2 and 2/2. So this area is going to be, what's the height of that rectangle? Well, the height of it's going to be the function evaluated at 1/2. So it's f of 1/2 times the base of the rectangle, or the width of the rectangle, which is 1/2. And then calculate the area of the third rectangle. And that's just going to be the function evaluated at 2/2. So the f of 2/2 times the width of the rectangle, which is a half. And then you calculate the area of the fourth rectangle. You say, hey, I'm going to calculate the area of the fourth rectangle, which is just going to be the function evaluated at 3/2 to get the height of the rectangle. And then we multiply by the width. So if we want to estimate the area underneath the curve f of x, we could estimate that area with these 4 rectangles. And the area that we get won't be correct. It's an estimate, so we expect it to be off. And in particular here, I want to notice that each little corner of these rectangles we're using to estimate the area is above the curve. So in fact, this is going to give us an overestimate of the area of, the area under the curve. And that's all right, because it's an estimate. So what I could say is, well, the area under the curve is approximated by those 4 rectangles. And then what is the area of the 4 rectangles? We need to take the area of the first plus the area of the second plus the area of the third plus the area of the fourth. And those 4 areas, we've calculated them right here. So it's just a matter of replacing a sub 1, a sub 2, a sub 3, a sub 4 with the area calculation. So it's the height of the first rectangle times its width, plus the height of the second rectangle times its width, plus the height of the third rectangle times its width, plus the height of the fourth rectangle times its width. That's a 3 in there. And then what we want to look at this and recognize, we can replace this with sigma notation from our previous homework. I want to notice that the numerators are incrementing 0, 1, 2, 3. So I could actually replace this with the sum from I equal, the first numerator is 0, the last numerator is 3. They're incrementing by 1s. So I could replace this with the sum from I equals 0 to 3 of f of I over 2 times a half. So I can replace my area estimate using sigma notation. And I could also ask myself the question, well, if I wanted a better estimate, what could I do? And what you want to notice is that if you just used more rectangles, so if we made the width of each rectangle smaller, we could get rectangles that fit the curve better than they currently do. So the way you improve the estimate is by improving the number of rectangles you use to estimate the area under the curve. And eventually what we're going to want to do is take the limit as the number of estimating rectangles goes to infinity. So here I have my summation, my sigma notation, giving me the area of the 4 rectangles that I'm using to estimate the area under the curve f of x. And once we have it in summation notation, we don't need to see the picture anymore to evaluate the summation. So I'm going to go to the next slide to give myself some room to write. So on the previous slide, we said, hey, we can estimate the area under the curve. by taking the function height times the width, function height times the width, function height times the width for each of the 4 rectangles. And we identified that we could put this into sigma notation. So we wound up getting f of I over 2 times a half, the sum of that from I equals 0 to 3. And we have a previous homework assignment where we learned how to evaluate a function using sigma notation. And the tool that we used was our summation formulas. So I've included 4 of the summation formulas here to help us remember what needs to be done. And remember from that previous homework assignment, our shortcut formulas for calculating summations all started with a lower bound of summation of I equal to 1. So each summation formula required that we start with a lower bound of summation at 1. And here I want to notice my lower bound of summation is a 0. So in the previous homework assignment, we said, hey, we can start to simplify things. Hey, I want to notice that 1/2 is a constant, and we know that constants can be factored out of the sigma notation. And I know that to use my summation formulas, I need to start at a lower bound of summation of 1. So I need to change the bounds of summation. So if I increase the lower bound of summation from 0 to 1, if I increase it by 1, I need to increase the upper bound of summation by 1 as well. So instead of going from 0 to 3, I'll go from 1 to 4 so that my lower bound of summation is set at 1. So the distance between the two numbers has to remain the same. So 3 minus 0 is 3. 4 minus 1 is 3. And then we need to adjust our I factor to account for the fact that we increased our summation index by 1. And if we increase our summation index from 0 to 1, we're going to need to subtract 1 to counteract that. So the idea was, from our previous homework assignment, when we plug in this lower bound of summation, we plug in a 1 for the I, we get 1 minus 1 is 0. That needs to match the original bound of summation. When I plug in the upper bound of summation, plug in a 4, I get 4 minus 1 is 3. That 3 needs to match the original upper bound of summation. So in this case, I increased I by 1. I increased it from 0 to 1. So to counteract the fact that I increased it by 1, I need to subtract 1 or decrease I by 1 in the function notation. And then what we saw in the previous homework assignment was that we could then rewrite the summation. This is the sum, 1/2 the sum from I equal 1 to 4. We can put the I minus 1 over 2 into the function. And remember from the previous slide, the function we were working with was negative x squared plus 4. So everywhere we see an x in the function, we'll replace the x with I minus 1 over 2. So I'm going to get I'm going to put a parenthesis here to hold my function in. I'm going to get the opposite of x squared, but the x gets replaced with I minus 1 over 2, and it's plus 4. And then I want to actually square this term out, so I'm going to get equals 1/2 the sum from I equal 1 to 4 of the opposite of. So if I square out the numerator, I'm going to get I squared minus 2I plus 1, squaring the denominator, over squaring the numerator, and then squaring the denominator, I'm going to get 2 squared is 4, so this will all be over 4, plus 4. And then to add, here I see that I have a constant term in the numerator. I'm going to want to add that constant to the existing constant. So I need a common denominator. So I'll change this 4 to 16 over 4 so that everything's over 4. So I'm going to rewrite my summation. This is 1/2 the sum from I equal 1 to 4 of, I have a negative I squared. I'm going to distribute the negative sign into the numerator. So I get negative I squared, negative, positive 2I. I get negative and positive is negative 1 plus 16. So negative 1 plus 16 is plus 15, and this is all over the common denominator of 4. But that common denominator is a constant, and because it's under all of the terms, it can be factored out. So instead of a half, I can pull the 1/4 out and get 1/4 times the 1/2 is an 1/8, which will leave me just the numerator terms in the parentheses. And then I can start to use my summation formula tools to break this apart into individual summations. So I'm going to get 1/8 times. So now we'll focus on the negative I squared. So we're going to get the opposite from the negative sign, the opposite of the sum from I equal 1 to 4 of I squared. So that takes care of the first term. Plus, now I'm going to get, I have a constant multiple of I, so I'm going to get 2 times the summation from I equal 1 to 4 of the I term, plus I have the sum from I equal 1 to 4 of the constant 15. So that's using properties of summation that we looked at in the previous homework. And now I can continue to simplify things. I can say, hey, the area under the curve, I'll just call it the area, is going to be approximated by the stuff that we have here. So this is 1/8 times, I have the opposite of, and I have the sum of the I squareds from I equal 1 to 4. So my summation formula for I squared is from the sum of the I squareds from 1 to n. So in this case, the n is equal to 4. So we have the case where n equals 4. So we're going to get 4 times 4 plus 1 is 5 times 2 times 4 is 8 plus 1 is 9, and it's all over 6. Plus, we're going to get 2 times, and now we have the 2 times the sum of the i's. So the sum of the i's, when the upper bound of summation is 4, is just going to be n equals 4. So we get 4 times 4 plus 1 is 5, all over the 2, plus this last one we have the sum from I equal 1 to 4 of a constant 15. So it's just going to be the constant times the n, or just 15 times 4. And then it's just a matter of simplifying things like we did in the previous homework. So this is going to equal 1/8. And here I see 3 goes into 9 3 times, and 3 goes into 6 twice, and 2 goes into 2 once, and 2 goes into 4 twice. So I get 1/8 times the opposite of 2 times 5 is 10 times 3 is 30, plus 2 divided by 2 is 1, so we get 1 times 20 is 20, plus 15 times 4 is 60, equals 1/8. We get negative 30 plus 20 is negative 10 plus 60, and we get negative 10 plus 60 is going to be 50. That's 50 over 8, and we see that 2 goes into both the numerator and denominator evenly. So 50 divided by 2 is 25, and 8 divided by 2 is 4. So the area under the curve is approximated by 25/4. And again, that area is an overestimate of the actual area, and we can improve that estimate if we wanted to by making n larger, making the number of rectangles we use larger. So in the next video, we're going to do the same thing with the same function, except we're going to look at estimating the area under the curve using right endpoints instead of left endpoints.